My name is Philip Reames. I'm here today to share an update with you on where we stand in terms of optimizing multiple exit loops. Before I dive in, I want to make sure I make a clear point, which is I'm going to be talking about the work not simply of myself, but of multiple other people over the last couple of years. Some of the people who contributed in this area were deliberately collaborating on this effort. Others simply happened to check in changes that were beneficial. Where appropriate, I have tried to list at the bottom of every slide the approximate date and who the contributors were. If I've missed anyone, my sincere apologies. With that, let's go ahead and dive in. Just to give a little bit of terminology so everybody's on the same page, if you're not super familiar with LLVM's loop terminology, a loop in LLVM is a cycle in the CFG that has a single basic block which dominates all of the other blocks from the loop. This is a key point. In particular, there may be cycles in the CFG that are not loops in LLVM's terminology. The basic blocks within a loop that contain branches that leave the loop are called exiting blocks. The blocks that they branch to are called exit blocks. The block that contains the source of the back edge will be the latch, and then outside of the loop, branching to the header will be the loop predecessors. If there's exactly one of those and the edge has a single critical edge, it will be a pre-header. There's a lot more information on the various terminology in use here in the docs if you're curious. Some bits of terminology that we're going to use in describing a few of the transformations here is a categorization of various loop exits. We start with the simplest ones, which are loop invariant exits. These are exits that depend on some condition that is defined outside the loop. A computable exit is any exit for which we have a closed form solution, whereas a variant exit is all of those for which we can't find a closed form solution. Particular example I happen to give here is the data dependent exit, but in general, a variant exit is any uncomputable exit. One key point here just to keep in mind is that this describes a branch in a point in time. It is entirely possible what initially is a variant exit is later optimized into something that is computable or invariant. So for instance, in the example I gave, maybe the loop varying address actually points to a constant buffer, and we're able to determine exactly when this branch exits the loop. Worth noting is there's also parallel extensions to non-exiting branches for internal control flow in the loop. That is mostly out of scope for our discussion today. So our starting point for today's talk is going to be roughly 2017. That is essentially the last time we gave a meaningful update in any of the LLVM dev conferences, so I decided that was a fairly decent point to start. At that point in time, we'd updated LICM and unswitch to be able to handle multi-exit loops. That gives us the ability to mostly eliminate invariant exits. And then there'd been some preliminary work done in Invar simplify, which is the core pass that eliminates uses of induction variables. And we handled some of the cases for multi-exit loops, but not others, as we'll talk about today. But the majority of passes in LLVM had checks that looked like what we see at the bottom of the screen here, where essentially we checked to see if there was a single exiting block, and if there wasn't, it just gave up and moved on. The other things we had at that point is we had two checked-in passes that tried to form single exit loops by canonicalizing multi-exit loops. The first one was induction range check elimination, which works by forming the classic pre-main post loop structure. The key point being that the main loop would hopefully have no remaining computable checks in it. The downside of IRCE, beyond the fact it's proven somewhat correctness risky and we keep finding bugs, is that it requires code duplication 3x. The other core approach that's been checked in and used pretty widely is loop predication, which comes out of the just-in-time compiler world. The basic idea of the loop predication transformation is to analyze the computable exits and to form a loop invariant condition that determines whether some particular exit will be taken. And if it is, fall back to the interpreter or lower tier of execution before actually entering the loop. This relies on the ability to speculate and fall back, so as a result, it's not usable in static compilers. This overall approach actually works fairly well. There's a reason we're sitting here today and having this talk in 2020 as opposed to about 2015, 2016. The downside to this approach, though, is that the results are fragile. So what I mean by that is that when they work very well. We eliminate all the exits, we get to the vectorizer, we get nice vector code, everything is golden. When it doesn't work and we miss even a single check, we tend to emit very, very poor quality code. The major reason thereof is pass ordering interactions where we just, we miss that one branch we could have discharged and didn't. And then, as I said, we hit the vectorizer, but this time we do nothing. This called for somewhat of a change of approach. And that approach is going to be what we're going to be covering today. And it's been the work of the last couple of years, where the basic idea is to have all of the existing loop passes natively handle multiple exits. First of all, so that there's graceful degradation. If we do get sort of a structure into, say, unrolling, we'll be able to unroll the loop. But also so that there's less sensitivity to pass ordering in multiple ways. The first example we're going to talk about is in LICM, which is loop invariant code motion. And there'd been a lot of work on LICM before we got into the 2017 timeframe. But I'm going to mostly not talk about that. If you're curious, there's some previous talks and things of that nature. The main limitation we had left in LICM was we weren't precise in analyzing exceptional side exits. So in the example here, we've got a branch that is conditional on a simple induction variable and the load of a length from an invariant memory location. The challenge for LICM is that LICM has to be able to prove that we can hoist this load without introducing a fault to the program. And historically, LICM essentially gave up if it encountered any exceptional instruction that might result in an exceptional exit from the function in the loop. Back in 2018, this was extended via the ordered instruction infrastructure to be able to reason about the order of occurrence of instructions, and we can now handle this case, hoist the load outside of the loop, and turn what, as written, is a varying condition into a loop invariant condition. Just worth noting, this was originally done via the ordered instruction infrastructure. Much more recently, we have extended LLVM's basic block with the notion of instruction ordering. And as a result, this is now directly working off of basic blocks rather than off the ordered instruction infrastructure. Moving into Invar simplify, the first transformation we'll discuss is linear function test replace, LFTR. This is a long-standing nomenclature that exists for single exit loops in the optimizer. The basic idea of LFTR is you're taking a induction variable and a exit branch that is in forms of a less than or greater than check, and we're converting it into an inequality check. So in this example, we go from the less than IV sent in to IV not equal to in. When we went to actually do the multi-exit support here, we stumbled across sort of an interesting problem, and it actually stumbled across this from bug reports at about the same time for single exit loops, which is it turned out that the transformation as written had a serious correctness flaw. Specifically, it was not correctly reasoning about poison and undef semantics. And one of the things it would try to do is do pre-increment to post-increment conversion. So that's adding, taking an exit test and shifting it from testing I to testing I plus 1, essentially. When it did that, it was not accounting for the fact that the two increments could potentially overflow, and it was converting well-defined loops into loops with undefined behavior. The end result was we basically had to rewrite the entire transform in the process of adding the multi-exit support. This was done back in May and July of last year. Elsewhere in Invars, we have another transformation called rewrite loop exit values, or RLEV, where the basic idea of this is we're trying to eliminate uses of instructions defined in the loop. So in this particular example, we have a use of IV that is, outside the loop, and then we're able to leverage the information about the exit condition to tell us that the value of IV outside the loop at that exit block is actually %in, which is the loop invariant expression. The main work here was not actually adding support for multi-exit loops at all. It was the fact that we had not handled the case where we had a mix of exiting blocks, some of which were computable and some of which were uncomputable or variant. I do want to mention in passing that this transformation has challenges with cost modeling, and it's unclear whether this is a canonicalization or should be an optimization and profitability trade-offs thereof. This work does seem to have magnified that existing issue a bit. It'll be one of the items we'll come back to a little bit later. One of the newer transforms in Invars is we now have a form of loop predication that works for static code without needing the despeculation ability that comes from running with a just-in-time compiler. So the basic idea remains the same, that we have some set of exiting blocks that are computable, and we're going to rewrite the conditions to turn it into a loop invariant condition if legal. So in the example here, I rewrote only the first of the two under the assumption that the second was, say, illegal to convert. Just to say a little bit about that legality, this is only a legal transform when we have a read-only loop with no side effects, and there's no value defined in the loop that is used along the exiting edge. The key reasoning here being that we have to be able to be sure that changing the iteration count at which we exit is not visible, because we're actually shifting the exit count from being in to being the first iteration. The effect of this is that we turn a computable branch into a loop invariant one, which as a result makes both unswitching and peeling greatly more powerful. As an aside, this is specifically powerful because LLVM has only peeling from the beginning. If we supported peeling from the end of a loop, loop predication will be much less useful and less impactful. I do want to just take a moment and say this work was very much inspired by the work that was done on the original loop predication pass, and that the loop predication pass is still in tree and still useful because it is more general and doesn't have the requirements around read-only loops for target or for front ends that can have the ability to despeculate at least. While working on Invars, which is scalar evolution based, we of course stumbled across a bunch of gaps in the existing analysis. One of the first and largest was it turned out that scalar evolution had a couple of exponential compile time issues. Specifically, we'd end up creating exponentially sized SCEVs in terms of the original IR. That has now been addressed through a series of patches that essentially added limits on the expansions. So that is, now mostly resolved. A second set of issues we ran across is that SCEV was missing a lot of simplifications around min and max expressions. This is particularly very relevant for multi-exit loops, because if you think about what a multi-exit loop that has multiple computable exits look like, the trip count for the loop as a whole ends up being a min expression of multiple SCEVs. So failing to simplify those ended up resulting in us being unable to perform transformations, or at least producing very suboptimal code when we did. The other major category of work here is around handling non-canonical forms of IR. The first one, it turned out there was a difference between the old loop unswitch pass and the new simple unswitch pass in the new pass manager. The second one is it turned out we were relying on canonicalization from SDiv to UDiv, and the same for SRIM and URIM. The main reason to fix things like this is it means that we have less sensitivity in pass ordering, and thus a higher likelihood of being able to get a positive result in the end. One small change I want to mention, because it's probably the biggest takeaway for anybody in this audience, is we've extended the analysis output for the scalar evolution pass to include the exit counts for all of the individual exiting blocks within the loop. So if you look at this example, we have some loop in a function foo, where we have a known exit count for do body, a known exit count for if end, and a uncomputable exit count for the latch. But interestingly, we have a upper bound in the exit count for the entire loop of 4096. If you see something like this, this is a good example to be moderately suspicious of, and to open the IR and go take a look exactly at what the exit condition of latch is, because there's a good chance that there's a missing simplification in SCEV on this example. Because we've been able to conclude through one set of reasoning that we have a very small an exit count. On the other hand, we don't have a closed form solution for that exit count. That's a little suspicious. So moving on, we're going to talk about peeling and unrolling. Starting with peeling, we have in tree all of the mechanisms for peeling multiple exit loops, but the actual usage thereof is fairly restricted. At the moment, we're only peeling multiple exit loops, where one of the exits is the latch, and the other exits are branching to blocks that end in deoptimize. Deoptimize is the despeculate construct I'd mentioned for just-in-time compilers. One of the areas that definitely needs some work, and we'll touch on this a little bit more, is cost modeling to be able to turn this on more generally. Moving on to unrolling, we now have full support for both runtime unrolling and static unrolling. The runtime unrolling work was done back in 2017, though I do need to note that this is apparently still off by default in upstream. We've been running with this enabled downstream for a while now, but again, cost modeling has not quite been worked through upstream. More recently, support for full and partial static unrolling has now landed as of last month, or a couple months ago actually. That is enabled by default. So where that leaves us today is we've gone ahead and updated sort of LICM and Invars and peeling and unrolling to all handle the case of multi-exit loops. Invars has been audited as complete. The others, so they're mechanically complete, but cost modeling is still a challenge. A couple of things that have come up while doing that is in Invars, LFTR and RLEV are canonicalizations that we sometimes produce suboptimal code as a result of. So there's a very active debate as to whether these should in fact be canonicalizations and if we need some form of undo pass later in the optimizer, or if these should be profitability-driven optimizations instead. Another major area of current consideration, and if somebody is interested in tackling this problem, I would be very, very welcoming, cost modeling for peeling and rolling. Specifically, there is a very delicate balancing act between the code size, particularly code size in nested loops, and the performance benefits we get from peeling and unrolling. Today, the cost models we have, in my opinion, are rather aggressive, and we peel and unroll more than is actually warranted. A noteworthy sort of analogy here is unswitch, where in the old unswitch that existed in the old pass manager, we unswitched very aggressively. And in the simple loop unswitch that we use in the new pass manager, we only unswitch if doing so increases code size by a very, very low amount. That is probably a worthwhile idea to continue sort of in the context of peeling and unrolling, but we need somebody to go ahead and do that work. And unfortunately, it's a very pragmatic, very much a measure and see type of approach, and quite challenging. Another area that there's very definitely room for active work on, there's more passes that we still have pass ordering interactions that we witness. The main one that we're stumbling across right now is the vectorizer. There's been some beginning of some work started on this where we've added a couple of sort of particular examples of things that we've seen that have made it from other passes into the vectorizer. Just to be clear here, the issue that happens here is you get some construct the vectorizer doesn't recognize or cost models inappropriately. And as a result of that, we generally only get one shot at vectorization. So even if some other paths could have handled it, it's really profitable or really worthwhile to have the vectorizer be able to at least understand it and perform the vectorization, even if later passes then clean up code that turns out to be less optimal than it could be, as long as it was still a profitable vectorization. Finally, we have a number of passes that simply we haven't gotten to yet. The main ones are loop fusion, distribution, interchange. I personally have not looked at these much at all yet, just because they don't tend to be that important in the workloads that I'm looking at. If anyone is interested in standalone work in this area, each of these would be independently, I think, a relatively straightforward project to pick up and continue. So overall, at this point, I think we're fairly comfortable with where we stand in terms of our ability to handle multi-exit loops. The general approach of going ahead and handling multi-exit loops first class has given us a lot more robustness and performance. The general strategy still remains to try to eliminate them where possible, but as a fallback, go ahead and be able to peel or unroll or otherwise, perform the transformations of the loop that we would like to, as if we'd optimized away the multi-exit loops and then come back to it and handle them afterwards, or at the very least produce code that's not absolutely terrible. That's sort of where we are today. If you have any questions, I'm happy to take your questions at this time. Thank you very much.
Hello and welcome everyone. Thank you, Philip, for a great talk. That was really interesting to see the overview and to see the work being done put into perspective. Now we'll have about 10 minutes of live Q&A. You will have a chance to type in your question. I will be reading the questions and I will be reading them to Philip. So we already have some questions. Let's dive in. And the first question is, what do you think about using max obj size? It's a new attribute soon to be proposed to limit the trip count because out of bounds access is undefined behavior.
Let's see. So I think this is actually a really good idea, but it ties into a related problem, which is that we actually have many sources of information about maximum object size. So to use like a small example, we might have a global constant, or we might have an aliquot that has a fixed size. And we need to be able to find an access that actually is provably out of bounds to be able to use the UB fact. So while having an additional attribute is useful, it certainly gives us a new source of information. We need to have the basic logic to reason about the out of bounds access, and in particular, analyze it and reason about it efficiently, that's going to be the core challenge. I believe that there's some existing code in Invar Simplify that does some very limited cases of this today, but extending that into a more extensive analysis would be the primary work required.
Okay. The next question is, are there other common loop constructs that you think would warrant a similar effort?
So let's see. So when I saw this one come in, I had to stop and think for a moment, because there's a number of ways that we canonicalize loops. Some of the obvious ones are as we canonicalize into a single back edge form, where you have loops that have sort of multiple back edges. We canonicalize it into a form where we everything branches together, and then there's the back edge. We also tend to like conditional latches as compared to unconditional latches. There are various optimizations that fail out if they don't see a conditional latch. I'm not sure any of those are worth pursuing, or at least I haven't seen lots of examples where they come up. I guess maybe the other form that might be useful to handle more generally is loops with interesting internal control flow. Many of the things that can be expressed as early exits can also be expressed as internal control flow of the loop. And there's probably interesting opportunities to better optimize such constructs in general, particularly in places like the vectorizer.
Okay, so the other question is about cost models. Do you have any specific cost model cases in mind which we need to care about, or we mostly have accurately throughput models but have code size issues falling out of it?
Let's see. So do I have a canned good answer to this? Unfortunately, not really. However, what my experience has been is that we spend a good amount of time looking at cases where either we didn't unroll where it'd be profitable to do so, or we massively unrolled or peeled and created a code size problem when the profitability of doing so was rather clear. The general sort of take I have is that we need to take a systemic look at our cost modeling around some of the loop transformations. The most obvious and problematic ones are unrolling and peeling, but this is also true of a bunch of the sub-transformations of Invar Simplify. As an aside, the new unswitch is a lot better in this respect than the old unswitch was. And it's actually one of the things I think might give us a hint as to possible directions to explore in looking at how we structure cost models for other loop transformations.
Okay, the next question is, what are the trade-offs of canonicalizing loops to just have a single exit versus making every single loop pass handle multiple exit case?
So let's see. So the trade-offs here are sort of multifaceted. The first one is it may not actually be possible to canonicalize to a single exit, or at least it may not be practical. That ties into the second reason, which is that if you rely on a strict canonicalization model, you end up with pass ordering problems being a major issue, where, if you have a loop that could have been canonicalized into a single exit form, but you happen not to catch that early enough in the optimizer because there's some other optimization that has to happen first to reveal that fact. Say some arbitrary transform and ends combine has to run to expose enough information. You end up sort of with a situation where you get one shot, and if you miss it, you get really terrible code out the back end. The other point is that to canonicalize to a single exit case, you have to generally generate code above the loop to generate a loop invariant expression that you then clamp the loop to. And again, profitability of that is not always clear. And today we do that pretty aggressively, but there's a question of whether we want to keep doing that long term. And if we don't, we definitely have to make sure that all of the other transform passes understand multi-exit loops natively.
Okay, the next question is, does SCEV or something else have an API to just check if a loop may be infinite or not?
So SCEV struggles with the concept of infinity. There isn't a direct representation of infinity in the SCEV language. So as a result, all of the accessor routines that give you, for instance, what is the trip count of this loop? When will it exit, etc. If the answer is infinity, SCEV can't really give an answer. The way we've mostly handled that instead is to have in transforms like Invar simplify to reason about the branch conditions on the exit to sort of prove that some condition can never be true. SCEV does have the sort of predicate reasoning, and that can be used on a branch by branch basis to prove that a particular exit cannot be taken. But there's no generic way to ask whether a loop is provably finite.
I see. And the other question is, do you think that a PGO or auto FDO profile can help loop passes to speculate on loop trip count?
So in short, yes. However, a estimated trip count and a proven trip count are two different things. And you can't, for instance, use a estimated trip count to eliminate exits in a loop or to perform other semantic transformations. They are really helpful for potentially driving the cost modeling of, for instance, peeling or unrolling. Knowing that what you're analyzing is a very hot loop, it may be worth doing slightly more code size than if what you're looking at is a cold loop. And then in particular, if you have internal control flow in the loop, being able to tell which portions of it are hot and not, and as a result, which branches are most interesting to eliminate through unrolling or peeling, I think could be very interesting in the cost modeling context.
And I think we already have some of the passes like unroll use this kind of information.
So I think you're right as well. I just couldn't remember off the top of my head what of that was upstream and what of that was downstream. I do know that we have at least some code upstream to preserve the profile, but I'm not sure how much that feeds into the actual cost model. I just don't remember.
Looks like we've exhausted the questions on Hoover. I actually had one question while I was watching the talk. You mentioned that LFTR is a canonicalizing transform. So we take a comparison which is in the form of less than or greater than, and we replace it in the form of inequality comparison. But to me, on the surface, it looks like we are somewhat losing, or maybe not losing, but when we have a comparison in the form of less than, greater than, we have information about the range. But when we have a comparison in the form of inequality, now we need to analyze the loop, analyze the induction variable to figure out the same fact. Why do we think that this is a good canonicalizing transform?
So LFTR, just as an aside, does two related transforms. One is the one you mentioned. The other is it does pre-increment to post-increment conversion. Personally, I'm sort of the opinion that these should probably be separate transforms and that we should reason about them separately in both their profitability and their advantage as canonicalization. LFTR has been a canonicalization in the mid-level optimizer since before I joined the LLVM project. So I don't really know the history of why we originally decided to make it so. I also agree that the removal of the obvious range facts is a little suspect, mostly not so much how it interacts with loop transformations based on SCEV, but how it interacts with things like correlated value propagation and known bits, which can get more information from the ranges than from the equalities.
Okay. It looks like we have 1 minute left. So I would say thank you, everyone, for joining the session, for submitting your questions. And we encourage you to continue the conversation on the community board on Whova and in roundtable sessions. Thank you, Philip.
Okay, so I have a couple seconds left. I will mention one minor correction in the talk. I'd said that the runtime unrolling was disabled by default. That was a misreading by me of the code in question. It's actually enabled upstream.